Here's a prototype I wrote a few days ago. Its purpose is to export scalable vector graphics from Draw.io documents and add hyperlinks to create interactive diagrams. I think the code is not a complete mess. It got some smaller functions to encapsulate details, but it also has some issues which are quite common when violating the single responsibility principle. Let's assume two developers are working in this project. One is working with the domain expert and is implementing all the application logic like analyzing the diagrams and deciding about proper references. The other one is working with the UX expert, realizing all requests for best user experience. As both aspects are completely mixed in this codebase, the developers will face merge conflicts frequently. Before launching this code to production, we definitely want to add some tests to ensure that the code is working as expected. While this code could certainly be tested as is, these tests would probably be unnecessarily complex and less focused as the application logic is coupled with technical details. Furthermore, with the current design, the application logic cannot be reused in other contexts easily, for example a web application, as details like file I/O are embedded into the application logic. The root cause of these, and even more issues, is the violation of the single responsibility principle. So what exactly does the single responsibility principle state? The name single responsibility principle seems to imply that a module should do only one thing. While this certainly applies to functions and methods, this is not exactly true for classes and modules. The most common definition of the single responsibility principle for classes and modules is a class should have only one reason to change. Sounds meaningful and correct, but what exactly are reasons to change? When thinking more closely about it, it turns out that software systems are changed to satisfy their stakeholders. These stakeholders effectively are the reasons to change. Different stakeholders have different roles, resulting in different perspectives on the software system, leading to different requests for change. The domain expert requests changes of the application logic. The UX expert requests changes to the look and feel of the application. The operator requests changes to support flexible deployments. And the architect requests changes to keep the technology stack up to date. In summary, the single responsibility principle states a module should be responsible to exactly one stakeholder or one role. Now there are roles and their reasons to request change, which are quite obvious, so we want to separate those almost always right away. Let's start with application logic and input-output operations. Examples of violating the separation of these reasons for change are reading and writing files directly in the application logic, database stored procedures containing business logic, and calling external services directly from the application logic using, for example, HTTP. This code is guilty of mixing file operations directly with the application logic as shown earlier. So let's separate these reasons for change. Therefore, I'm going to create a class called PageReader, and I'm going to pass the input file to the constructor. Then I'm going to create a method called readPages, which is independent from any I/O. This method will then be responsible to read the file, parse the XML, and return all the page names. I'm also applying my favorite naming conventions to the generated member. Okay, now let's move on to the second violation of I/O operations within the application logic. In order to extract the process start call from the application logic, I'm going to create another class called SVG Exporter. I'm again passing the input file to the constructor together with an output folder. Let's generate the class and move it to a separate file. Now I'm going to move the process start call into the SVG exporter. Therefore, I'm going to create an export method which returns an SVG document. Let's fix the argument name and paste the process start call. We can now also encapsulate the path to the Draw.io executable inside the SVG exporter. I'm again applying my favorite naming conventions to the members. And I'm then introducing the SVG document required by the caller. The SVG document will be a record type containing the name and the content of an SVG document. Let's add the missing usings. and create an instance of the SVG document. This shows that the export method requires another parameter, which is the page name. So let's add it. Now I can complete the creation of the SVG document. Finally, I'm fixing the generation of the SVG file name. And of course I also have to adapt the caller to the changed signature of the export method. Now that the remaining file I/O operations are also encapsulated in the SVG exporter, I can clean up the application logic by using the SVG document. So I'm passing it as an argument to add links, and I'm going to adapt all the usages of the previous parameters. Finally, I'm adding one more API to the SVG exporter to save an SVG document back to the file system. To keep the implementation of the save method simple, I just take over the code previously used in the application logic. Okay, this code already looks cleaner, but this file still combines two responsibilities I like to separate in this step as well. On the one hand, it contains the actual application logic, and on the other hand, it acts as the main component which composes the different classes and modules of the application. To separate these responsibilities, I'm going to create a new class called SVG Processor. Let's generate this class and move it to a separate file. Let's also generate the method addLinks to this new class. And now I'm taking all the application logic and I'm moving it over into the SVG processor. Let's fix the missing usings and also the missing access modifiers. To finish the implementation of the SVG processor, I'm going to pass the pages collection to the constructor of this class. Let's introduce a member for the available page names so that we can access those from the implementation of the class. Oops, I forgot to add the proper access modifier. And with this, the application logic is separated from the composition code as well. Now testing becomes that simple that there's hardly any excuse to not do it. So let's add at least one basic test. Therefore, I'm going to create a test case to check that links should be added for existing pages. As input for our testing, we also need an SVG document. Including a huge SVG string in the test directly might not look beautiful, but fetching test relevant data from other sources like an external file is something I like even less, as it makes the test harder to understand. I first create an instance of the SVG processor and I parse a collection of available page names which are system and parser. Then I'm going to call the API I want to test, which is addLinks, and I need to pass an instance of the SVG document record. So let's create one with the content provided above. In order to verify that the addLinks method is working as expected, I first need to extract the parser element from the SVG document. Then I'm going to verify that this element has a handler for the onClick event registered. Of course, I also need to add the test attribute, and Visual Studio Code is showing me that I can simplify this code here as well. Now let's execute the test. Oh, looks like the F# test controller has some issue here. Let's ignore this for now. But this test is also failing with the proper test adapter. What's wrong? I simply need to make sure that I'm fetching the most inner div element for this verification. Let's rerun the test. And it is green. Awesome. The requests to change the code for parsing inputs or formatting outputs typically come from different roles than those responsible for the application logic, so we want to separate these responsibilities accordingly. Examples of violating the separation of these reasons for change are parsing strings into structured data like datetime inside the application logic, or formatting data structures as for example HTML inside the application logic. The concrete violations in this codebase are parsing the display text of an SVG element and formatting SVG elements with specific CSS attributes. I start extracting these responsibilities by creating another class called SVG Caption Parser. And I'm going to create a member for this class right in the SVG processor. I'm then taking the existing getDisplayText method and I'm moving it over to the SVG Caption Parser. And I'm moving this class to a separate file as well. In order to address the second violation, I'm going to introduce another class, which is called the SVG Hyperlink Formatter. And I'm also going to create a member for this class in the SVG processor. I'm then extracting all the formatting code from the SVG processor and I'm moving it into the SVG Hyperlink Formatter into an API called ApplyStyle. And I'm going to move this class into a separate file as well. The last step of this refactoring is of course passing instances of the new classes to the constructor of the SVG processor. Okay, the responsibilities are organized way better now. However, there are two additional opposing perspectives that we always strive to keep separate within our codebase: functional versus non-functional requirements. Examples of violating the separation of these reasons for change are adding caching directly to the repository pattern implementation or the class performing expensive computations, spreading usage logging over all web controllers, or having authentication and authorization scattered across the entire codebase. This application does not have such violations yet, but if I would have to introduce some caching for performance, I would definitely use the decorator pattern to separate the caching logic from the data acquisition logic as explained in this video. Now here's the catch. Looking at a particular module or class, the different roles and corresponding responsibilities are not always obvious. If responsibilities are not changing independently, separating those would cause unnecessary complexity. Let's look at the heart of this application, the SVG processor. It still does multiple things. It finds page references, it adds the on-click event handler, and it applies the formatting. Are these responsibilities we should separate? Which different roles would request different changes at different times? In such cases, I recommend the following strategy. Keep it simple. Keep use case related code together. And then relax. Wait for the requests for change to occur and then apply the necessary refactoring. Imagine a software which allows visualization and analysis of complex graphs, such as the dependency structure within a software system. Such a graph consists of nodes and directed edges, which are kept independent from concrete rendering technologies like WPF or HTML. The actual rendering happens in the respective graph renderer. A simplified render function may look like this. So far, so simple. Now, for the next version of this software, a change is requested. It should be possible to group parts of such graphs into clusters. Unfortunately, the current design is not prepared for graph items other than nodes and directed edges. So to support clusters, we have to modify the existing render function. This change may look simple, but generally speaking, when modifying existing code, there's always the risk of breaking existing functionality. Furthermore, we have to find all the places like this where nodes or edges are treated separately, which always includes the risk of missing one of such places. And finally, depending on the change, it might be necessary to recompile and even to redeploy all depending modules. The fundamental issue of this design is it violates the open-closed principle, which states software entities, classes, modules and functions should be open for extension but closed for modification. This means it should be possible to extend the behavior of a software entity without modifying its existing source code, but by adding new source code. Sounds complicated? Here is probably the simplest example of the open-close principle you have most likely used uncountable times already. This function filters a collection of items. It accepts another function as argument, which defines the filter criteria. This function is closed for modification. Most modern programming languages provide such a function from their base library. And at the same time, this function is open for extension by accepting different filter criteria. That's not really complicated, isn't it? So in essence, the open-closed principle states that abstractions should be defined between the immutable behavior of a software entity and the behavior which is allowed to be extended or changed. In object-oriented design, we usually do not use functions to define such abstractions, but interfaces or abstract base classes. One of the classic design patterns used to apply the open-close principle to a module is the strategy pattern. Therefore, we define an interface of one or multiple methods and pass this to the module, usually through the constructor. The module then uses this interface to delegate decisions or actions to the implementations of this interface, and so allows the clients of this module to provide different extended behaviors in different contexts. Another classic design pattern used to apply the open-close principle is the template method pattern. Here a class allows extending its behavior by providing protected virtual methods, often also called hooks, which could then be overridden by different derived classes. Now that we know how to apply the open-close principle, where do we apply it? I mean, for a given software entity, different kind of changes might be required in future, which very likely require different abstractions at different places. Furthermore, applying the open-close principle is not for free. It takes considerable development time and effort to design proper abstractions, and those abstractions can increase the complexity of the software. So we definitely do not want to add abstractions everywhere just in case. This means we have to choose the kinds of changes against which we want to close our design. But how do we predict the future? On the one hand, we have to use our experience about the domain, our industry, the organization and our software system. On the other hand, we need to do some research and ask seniors and discuss with other team members. And we also need to interview domain experts and our customers. Finally, I would recommend to apply the open-close principle only for those kinds of changes which are almost predictable based on our research and experience. In all other cases, I would strongly recommend to take the first bullet, as Uncle Bob once said. That means we wait for the first change of some kind to appear and then derive an appropriate abstraction from this concrete use case to avoid further impact by similar changes in future. As this design tactic is quite reactive, we require fast feedback to make this approach work. The fastest feedback we will get from our tests, so we want to write them first. This not only ensures that our design has testability built in. Experience shows that abstractions created for testability will protect us from other kinds of changes later on. In order to get fast feedback from our domain experts and even from our users, we should aim for short development cycles and even frequent releases. Last but not least, I strongly recommend to develop features first and required infrastructural modules along with the features to ensure that the infrastructure provides the abstractions needed, but nothing more. So having taken the first bullet and equipped with all the new knowledge, how could we now apply the open-close principle to the graph renderer? First, we introduce an abstraction for the concrete use case of rendering different graph items. As the iGraph item interface already provides such an abstraction to specific graph items, we simply add a draw method. In order to keep the existing node and edge classes independent from a concrete rendering technology, we define the draw method as abstract in these classes as well. We then create rendering technology specific derived classes which implement the draw method. Finally, we adapt the render function of the graph renderer and open it for extension of new graph items. Now adding support for clusters does not require any code changes in the graph renderer. This design is also ready for future changes of similar kind, like undirected edges or nodes of different shapes. Let's start with the definition of the Liskov substitution principle. It states, if for each object O1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. That sounds pretty complicated. So what exactly does that mean? Here's a simple example. We have a class T and a class S which derives from T. The derived class S then only defines a new API. For this example, we can easily conclude that we can safely pass an instance of class S where an instance of class T is expected without changing the behavior of a given program. Hence, this definition of class S fulfills the Liskov substitution principle. Here's another example. We again have a class T and a class S which derives from T. But now S overrides the method foo defined by T and throws a not supported exception. As S derives from T, technically we could still pass an instance of S where an instance of T is expected. But even without knowing the concrete program, we can pretty safely assume that this exception would not be expected by the program, and so we have to conclude that S would change the behavior of the program. Hence, this definition of class S clearly violates the Liskov substitution principle. Okay, let's change this example slightly. Class S still derives from class T and also still overrides the method foo, but now it returns null instead of throwing an exception. If we now pass an instance of class S where T is expected, will this change the behavior of a given program? Does this definition of S violate the Liskov substitution principle? When trying to answer these questions, it becomes obvious that in essence, the Liskov substitution principle is all about contracts. In a design like this, the base type T establishes a contract towards its clients. This contract consists of the syntactical AP surface of T and, more importantly, its semantical behavior. The Liskov substitution principle demands that all subtypes of T must fulfill this contract as well. The importance of this demand becomes obvious when considering the consequences of violating it. For example, if subtype S3 violates the Liskov substitution principle and T gets substituted with S3, then clients of T may fail completely or misbehave in some way. That means, violating the Liskov substitution principle clearly is a recipe for building fragile software. Now, why is this all relevant for your software designs even if you don't use any inheritance at all? You might not use inheritance, but then you definitely use other concepts like interfaces and functions to define abstractions, as every non-trivial software requires such abstractions in order to abstract from implementation details, or to support variability, or to provide extensibility. From my perspective, the Liskov substitution principle is critical in these contexts as well in order to develop robust software. Now, having understood the importance of contracts, how exactly are those defined by the abstractions? Unfortunately, most today's programming languages are not much supportive here. While add-ons exist for some languages, we mostly have to rely on the documentation provided by the abstractions. In case of abstract base classes, we could inspect the implementation of the virtual methods additionally. Let's have a look at some examples of such contracts so that we can learn how to spot violations easily. In this example, the abstraction defines that an argument exception will be thrown in case of an invalid service name. The implementation, however, throws a different exception, which would only be valid if this exception would be a subtype of the exception defined by the abstraction. As this is not the case in this example, foo strategy violates the Liskov substitution principle. The Liskov substitution principle requires that preconditions are not strengthened by the implementation of an abstraction. Here the iRepository defines that the parameter items must not be null. The document repository, however, also rejects an empty collection, which breaks the contract defined by iRepository towards its clients, and so the document repository violates the Liskov substitution principle as well. The Liskov substitution principle also requires that postconditions are not weakened by the implementation of an abstraction. In this example, iRepository defines that findAll returns an empty collection if nothing was found. But the document repository returns null in this case, which very likely causes the clients of iRepository to fail and so violates the contract defined by the abstraction. Invariants are part of such contracts as well and must not be weakened by an implementation of an abstraction either. In this example, iSet defines that implementations must not contain duplicates. The simple back class violates this invariant as its add method does not check for duplicates at all. Another violation of the Liskov substitution principle. Adding new methods and even new fields in a subtype does not violate the Liskov substitution principle, as these new members are not accessible through the base type and so are simply not part of the contract. But if a subtype adds a new API which brings the base type into an invalid state, then this would be a violation of the Liskov substitution principle again. In this example, the value property of the base type cannot be changed to the base type API, but the new API of the subtype suddenly allows altering the value after object creation. Finally, effectively removing functionality from the abstraction also breaks the contract towards its clients, which is probably quite obvious in this example, but might not be that obvious in every case. So as a rule of thumb, empty implementations are a pretty clear indicator of violations of the Liskov substitution principle. Now that we know how to detect such violations, How can we fix those? In some cases, we can simply fix the implementation by ensuring all pre- and post-conditions as well as invariants defined by the abstractions. The design tactic to achieve this is called design by contract, which I have explained in depth in these two videos. In other cases, we might realize that an existing abstraction does not fit for all scenarios, so we need to refine the abstraction. We can achieve this by factoring out the common aspects into a new abstraction and then derive every specialization from the respective abstraction. Now we know how to detect and fix violations of the Liskov substitution principle, but wouldn't it be even better to prevent such violations? Here are some ideas. Instead of trusting every implementation of an abstraction to explicitly check defined preconditions, we could try to push such preconditions into parameter types. In this example, the condition that a defect ID must be greater than 0 is encapsulated in the defect ID class. Another approach could be to define some kind of a test bench which verifies the contracts defined by an abstraction against each implementation of this abstraction. Of course, this approach does not really prevent violations by design, but definitely helps to find such violations fast. And here's one more approach. In this design, the abstraction keeps control over the public API surface and ensures the validation of the contract explicitly. It then provides dedicated hooks, which need to be implemented by the derived class to provide the actual functionality. Of course, also this design is not bulletproof, but it definitely provides more governance than an API documentation of an interface. And this brings me to the following thought. Nowadays, we usually prefer interfaces over abstract base classes because these are cheap to create, are best supported by dynamic mocking frameworks, and allow multiple inheritance. On the other hand, abstract base classes offer more options to enforce contracts towards derived classes. From the perspective of the Liskov substitution principle, I wonder whether we should actually favor abstract base classes more often. What is your opinion? Let me know in the comments. So here's the definition of the interface segregation principle. Clients should not be forced to depend on methods they don't use. I don't see words like interface, base class, or inheritance in this definition. Do you? Nevertheless, let's quickly summarize the common explanation of the interface segregation principle, because it is definitely not wrong, it just is only half the story, as we will see in a minute. Suppose you have a design containing an interface with multiple implementations, or a base class with multiple derived classes. One day, you want to realize a new feature in this design, which requires an additional behavior to be added to some of the derived classes. In order to still be able to handle all derived classes through an abstract interface, you think of simply adding the new API to the existing common interface or base class. But this decision would be a clear violation of the interface segregation principle, because all current and future derived classes would have to provide an implementation for this new common API, whether those classes actually need this new behavior or not. Such a design would cause obvious code smells like empty implementations, questionable dummy implementations, or implementations throwing exceptions, which are not just a cosmetic issue, but can result in severe and hard to find bugs. The solution is, as the name of the interface segregation principle already implies, to create a new interface for the new behavior, which is then only implemented by those classes which really require this behavior. The client code of this design then either gets the proper interface directly injected or uses a cast to test whether a given derived class provides the additional behavior or not. So far so good. But as already stated, this was only half the story. Reading the definition of the interface segregation principle again, we can understand the word clients also as regular classes which use other regular classes or interfaces. And the word interface in interface segregation principle we can also interpret as the API surface of any given class. Now it becomes more obvious that the interface segregation principle applies to any design even if no inheritance or common interface is involved. Let's look at a concrete example. Imagine some application using a database. In order to keep the application logic decoupled from any concrete database technology, the repository pattern is used. This repository implements a single interface which provides the classic CRUD APIs to the application logic. So far, so simple. Now imagine one day we realize that we need to collect some diagnostic information about the database to allow monitoring and analyzing the health of our application. To query these statistics, we simply add another API to the existing repository interface. And with this pragmatic design decision, our design is now violating the interface segregation principle, as the diagnostics module depends on the full repository interface, including all CRUD APIs it actually does not use. Now you might ask, but if the diagnostics module does not use these CRUD APIs, what is the issue then? One effect of this design could be that the diagnostics module gains additional dependencies it actually does not need due to the types exposed by the not used methods of the repository interface. Furthermore, any change of the repository interface requested by the clients of the CRUD APIs can cause an impact on the diagnostic module, as every interface change is a breaking change for those classes implementing it. The diagnostics module might have a fake implementation for the repository interface to mock the actual database during testing. Assuming that the actual application logic and the diagnostics module are owned by separate teams, this interface dependency even results in a dependency between teams, which is probably quite unexpected from project and organizational perspective. Or consider tools and techniques which are based on static dependency analysis, like impact-based testing for example. Unnecessary module dependencies make such approaches either more complicated or less efficient. And last but not least, every change of the unused CRUD APIs requires an unnecessary recompilation and redeployment of the diagnostics module. In summary, violating the interface segregation principle results in a design where a change in one part of the system has unexpected side effects on other parts of the system. Now you might ask, are those really severe issues for my project? Maybe not in the beginning. Maybe you can simply compile, test and deploy everything all the time. But please don't forget that successful projects tend to grow in size and complexity and that team members might change. Such shortcuts, like violating the interface segregation principle, often appears harmless in the beginning but might grow into severe issues over time. So my general recommendation would be to be aware of the possible consequences of violating the interface segregation principle and to address such violations early on. And especially if fixing such a violation is actually pretty simple. We simply introduce a dedicated diagnostics interface. This small change alone already addresses half of the issues mentioned. If we now even move the interface into a separate package, we could also fix the unexpected module and team dependency. Of course, if the new diagnostic interface needs to be changed in future, this would still result in impact on its clients. But first, as the diagnostics interface is rather generic, we can assume it is more stable than the repository interface. And second, the dependency from the application logic to the diagnostics interface is not unexpected. It is even quite likely that there is an explicit requirement for the application logic to support the collection of diagnostics information. Now you might argue, wasn't that all obvious? Why would one add the diagnostic API to the repository interface in the first place? Well, there are some aspects to consider. Simplicity. Extending an existing interface is just simpler than extending an existing design. Time pressure. We are probably all guilty of having made compromises the last days before an important milestone, or simply not realizing the consequences immediately. Developers who never experienced the pain of design issues probably have a hard time detecting such design smells. So here are some indicators of possible violations of the interface segregation principle. Interfaces or classes with many APIs. Interfaces or classes where APIs form logical independent groups. Some implementations of a common API throw exceptions. Not all clients of an interface need all APIs. In summary, violations of the interface segregation principle can be detected when reviewing an interface from its client's perspective. Imagine a simple blogging software, which of course allows creating, editing and reading articles. It also provides a simple full-text search and a home feed showing recommended readings for each user. In order to realize these functionalities, we also need some database to store the articles. And of course we use our favorite ORM library because no one wants to handcraft SQL statements in 2023, right? Of course our application needs a web front-end, so we pick our favorite web framework, which allows us to set up the web UI in no time. The articles are edited and stored in Markdown, so we also need a renderer which converts the raw articles into a structured HTML document, which can then be nicely styled in the UI using CSS. Notice that with this simple and naive design, we have created a traditional layered architecture which builds an application on top of existing modules. And this is where the dependency inversion principle comes into the picture, which states high-level modules should not depend on low-level modules. Both should depend on abstractions. And abstractions should not depend upon details, details should depend upon abstractions. But what does that mean? In this context, high-level modules refers to those modules which implement the more abstract, higher-level functionality of our application, which are the business rules. In contrast, low-level modules refers to those modules which implement specific details of the application, the building blocks used to realize the higher-level functionality in a concrete context. And what about abstractions and details? Details are those aspects of a software design which are needed to make the application work in a certain context, but which are neither essential to its business value nor to its identity. Abstractions, on the other hand, are the business rules, the domain abstractions and other abstract concepts which define the business value and form the identity of the application. That having clarified, if we now compare our naive design with the dependency inversion principle, we have to recognize that our design entirely violates the dependency inversion principle. Our high-level modules do depend on the low-level modules, and our abstractions do depend on the details. But why is this a problem? To answer this question, let's answer this question first. Where is the business value of the application located in our design? As the high-level modules contain the business rules, which solve a business problem, clearly these high-level modules contain most of the business value of the application. Concluding this, do we really want our high-level modules to depend on details which are not nearly as relevant to our application? Imagine this. As initial data storage setup, we have decided for Entity Framework Core and some SQL database. And because we had to build up the application fast and we wanted to keep it all simple, we made the DB context of Entity Framework Core the primary API of our data access layer, which is now used in all high-level modules. But later it turns out that hosting our blogging software in the cloud based on the proprietary storage solution provided by the cloud provider would reduce the hosting cost of our application drastically. In our design, replacing one data access implementation by another, which is supposed to be a less relevant detail, would impact all our high-level modules. Or imagine this. A market analysis reveals that providing a native Android app additionally to our browser UI would increase the market acceptance of our application significantly. Supporting the operating system native front-end libraries requires a complete redesign of our low-level rendering module. And again, changes in a module, which is supposed to be a lesser relevant detail of the application, create severe impact on our high-level modules. So how can we use existing libraries and low-level modules without depending on those? We need to invert the dependency. Instead of allowing the low-level module to define the API through which a high-level module can interact with it, we shift the ownership of the contract to the high-level module. The high-level module now defines which functionality it requires from any implementation of this interface. It not only defines which APIs are needed, but it also defines the data structures passed through this interface. By this, the high-level module defines an abstraction, which now both the high-level module and the low-level module depend on. To apply this concept to our sample application, we first create an interface which sufficiently abstracts the data access layer by defining the needs of the high-level module. If multiple high-level modules depend on the same low-level module, these high-level modules need to agree on a common interface, which then would probably become an even better abstraction of the detail encapsulated in the low-level module. As the ownership of this interface is now shared among the high-level modules, this interface will be placed in a dedicated package. Looking at the direction of the dependencies again, we see that the specific data access technology has now become a true detail, which can be replaced without any impact on the high-level modules anytime. Now, although such a design makes it easier to reuse high-level modules in other contexts, at the same time, it has a significant drawback. Low-level modules are now coupled to the high-level modules, as the interfaces implemented by the low-level modules are defined in those high-level modules, which makes it harder, if not even impossible, to reuse the low-level modules in other contexts, for example in other applications. To resolve this problem, we apply the adapter pattern. First, we create an interface for the low-level module which is intended to allow reusing the low-level module in multiple contexts. We then create a new class, the adapter, and we put it into a separate module. The adapter then uses the interface of the low-level module to implement the interface of the high-level module. The adapter would also convert between data structures defined by the low-level module and data structures defined by the high-level module. This design certainly adds a bit of overhead and in some cases may even have some performance impact, but it keeps the high-level modules independent from the details and at the same time allows an easy reuse of the low-level modules in other applications. How can we apply this approach to our sample application? Suppose we want to reuse our Markdown to HTML renderer in other applications as well. And at the same time, we want the high-level modules of this application to be independent from this detail so that we could also support, for example, an Android native UI as suggested earlier. To achieve this, we keep the low-level interface of the renderer and add a new abstraction defined by the high-level modules. We then create the adapter in a dedicated module, which then uses the interface of the renderer to implement the interface defined by the high-level modules. Simple! It almost seems to be a bit too simple, isn't it? And in fact, we have to have a closer look at one particular aspect. When inverting dependencies and decoupling modules, we so far talked about and simply introduced interfaces. But actually, the dependency inversion principle talks about abstractions. An interface, of course, is an abstraction of a concrete implementation. But just defining an interface is often not enough to fully apply the dependency inversion principle and truly decouple modules. For example, an interface exposing conceptual details is not an appropriate abstraction. This class represents a document containing some content, but it also has a file name property and so exposes the conceptual detail that the document is stored in a file system. A more abstract solution would be to use a URI and to rename the property to location, which assigns a generic address to the document but does not expose anything about the storage technology. And if an address is not necessary in the given context, an even more abstract solution would be to just provide a name or an ID property and some API to access the content of the document via a stream. So generally speaking, finding an appropriate abstraction is more than just defining an interface. It is about finding or inventing a more abstract representation of a concrete aspect. This also applies to data structures used by this interface. A concrete aspect can often be abstracted in various different ways. An appropriate abstraction depends on a specific context or domain. An appropriate abstraction ideally tries to anticipate future changes to some extent, which definitely doesn't make it easier to find or invent one. So what does this mean for our sample application? How could an appropriate abstraction of the renderer module look like? How could we abstract rendering HTML on the one hand and rendering an article for an Android native UI on the other hand? One approach could be to define some data structures representing the abstract structure of a document. We could have a document type which has a title and a list of sections. A section could have a headline and a list of paragraphs. A paragraph could consist of a list of text blocks. A text block could be plain text with optional formatting, or a link, or an image. The actual renderer interface would then accept such a document, and the specific renderer implementation could then do the needful to render the document for the specific target device. This design would not only provide an appropriate abstraction to the existing and already requested renderers, but would also already anticipate possible future changes to some extent. Now that we have discussed in depth what the dependency inversion principle is, why it is an important design principle, and how to apply it to some concrete design, there is still one question left. Are there any drawbacks of applying the dependency inversion principle to a design? And as always, there is no such thing as a free lunch, so there are a few things to keep in mind. It can be quite some effort to develop the appropriate abstraction for a given context. And of course, this abstraction needs to be maintained additionally to the actual modules. When applying the dependency inversion principle together with the adapter pattern, the conversion between the different data structures could impact performance. Applying the dependency inversion principle with or without the adapter pattern is probably not the most intuitive design for many developers, and may so be considered as increase in complexity. And this brings us to the very last question of this video. So when should you use the dependency inversion principle? Me personally, I tend to start applying the dependency inversion principle rather early in the development phase of a project, definitely for third-party libraries. Some developers might consider this as over-engineering, but I made the experience that finding the right point in time to apply the necessary refactoring to invert the dependencies is not as easy as it may seem. Me personally, I have observed far too often that this point was missed and all the issues the dependency inversion principle would address started to emerge in the codebase. Nevertheless, if I would have to give a recommendation, here are my thoughts. Apply the dependency inversion principle to third-party libraries, specific technologies, and external services if your team has 3 developers or more, or your codebase is bigger than 10,000 lines of code, or your project has an expected lifetime of more than 12 months. Apply the dependency inversion principle to your own low-level modules if multiple teams are working in the codebase, or the project spans multiple source control repositories, or multiple applications are based on the low-level modules.